Think of nothing. What do you see? You might imagine a vacuum, a region of the universe drained of all matter and radiation. But go further. Try to think of a true nothing, an absolute nothing. This nothing is not just empty, but devoid of space and time themselves. Given our everyday experiences, this is hard to imagine. But we have often struggled with the concept of nothing. The biblical story of creation tells us that in the beginning, God created the heaven and the earth. But what existed before God's creation? In a moment before time, in a place before space? The Bible simply does not say. And indeed, our scientific theories and observations also tell us that our universe has not existed for eternity. They tell us that 14 billion years ago it had a beginning, a fiery birth in a maelstrom of particles and energy, and it has been expanding and cooling ever since. So what came before? Cosmologists offer tantalizing possibilities. Maybe our universe was begotten from a previous existence, part of an endless cycle, or formed in the violent collision between two other universes. But perhaps the most unsettling answer of all is that our universe was born from nothing. And if that is the case, how does one get something from nothing? Is no electron as real as 1 or 2? When electric or magnetic fields are at zero, are the fields still there? These might seem like strange questions to ask, but by the early 20th century, our notion of physical reality had become somewhat fuzzy. The rigid, clockwork universe of Newton had been replaced. Einstein had turned space and time on their heads with his theory of relativity, and experiments showed that the world of the very small was governed by a totally new set of physical laws. In the world of atoms and electrons, physicists spoke not of certainties, but of probabilities. Probabilities governed by brand new rules, the mathematics of quantum mechanics. But this is not how we see the world. Our macroscopic, large-scale world is one ruled by certainties, by things, by reason and logic. Nothing is nothing, something is something, and when you put your cup of coffee on the table, it stays there, every time. Yet the distant world of the very small, the world of quantum strange, in which something can be born out of nothing and matter can pass through matter, has more of an effect on us and the entire universe than we might think. To understand this, we are going to go on a journey across time and space. From the universe's first moments to its far-flung future, we are going to unpack the meaning of quantum mechanics, explore its impact on the cosmos around us, leading us to the biggest question of all. Just where did the universe come from? Werner Heisenberg had a nasty case of hay fever. As a young physicist, he had been trying to understand the rapidly changing landscape of early 20th century physics. For months, he had been attempting to piece together the seemingly nonsensical world of the atom. He understood that in an atom, electrons orbit a nucleus, but if these orbits were like planets orbiting the sun, the atom would collapse in a fraction of a second and simply cease to exist. So what rules governed the motion of electrons? Everything he had tried failed as his mathematics became unwieldy and unruly, and now his summer hay fever had hit. His head was becoming cloudy, his nose stuffy. He decided to escape. Seeking sanctuary on the small island of Heligoland, located in the North Sea, he hoped the fresh, salty air would clear his mind. And it was on tiny, isolated Heligoland, whilst relaxing one evening, that he was hit by a revelation that totally changed our understanding of reality. It had all begun in 1900 with Max Planck's desperate attempts to explain how hot objects glow. He knew that in hot objects atoms jiggled, and it was this jiggling that produced the rainbow of colours he could see. In classical physics, all possible jiggles were allowed, but to agree with experiments, Planck added a new, unexpected ingredient. He restricted the jiggles, so energies were present in distinct individual chunks. And in quantizing these jiggles, quantum mechanics was born. By the 1920s, this world of the very small, the world of atoms and electrons, had become a strange and complex place. Just like energy, the orbits of electrons appeared to be quantized too, existing at specific distances from the nucleus. And in 1925, Erwin Schrödinger wrote down his wave equation to explain quantum mechanics. Objects like electrons were no longer in a particular place. Instead, they were fuzzy and spread out, described by something known as a wave function. Heisenberg had been caught up in this swirling, heady mix of quantum theory. Like others, he was trying to bend well-established rules to explain how electrons orbited in atoms. Perhaps they underwent little oscillations, something Heisenberg knew how to calculate. However, like all attempts before, his calculations failed to explain what the experimenters were telling him. But in the cool, fresh sea air of Heligoland, new ideas quickly crystallized. He realized that we can never actually observe an electron in its orbit. What we see are the emitted frequencies of light as electrons from one orbit to another. So why bother trying to calculate the details of the orbit? He decided what we should calculate is what we can actually observe in our experiments. Heisenberg began working through the mathematics, ignoring how the electron was precisely moving, and it was then things came into stark clarity. His new mathematics worked. The form of the equations in front of him seemed strange, but a mathematician would have recognized them as matrices. Whilst these are common in physics today, they were still a novelty in the 1920s. Heisenberg did not sleep that night, instead setting off on a pre-dawn walk. He sat and watched the first rays of the sun peek over the horizon from a rocky outcrop on the island. As the day warmed, he realized he had a new mathematical way of explaining the world of the very small. But what a bizarre world he had found. Heisenberg's mathematics tallied with Schrödinger's. They did not talk of where an electron is, only where it might be. And when it came to an electron's speed, the description is equally vague. How an electron jumps from one orbit to the next was unknowable, just the energy emitted when it did so. And it didn't talk about the precise time an electron would make such a quantum jump, just the chances of the jump occurring. The quantum world was not a work of precision. The quantum world was one of probabilities. Staring at his equations, Heisenberg realized the vagueness in position and speed were in fact related. He saw that the more accurately we can discern a position, the less certain we are of speed. And if we try to accurately determine speed, the position is fuzzier. Imagine you put an electron in a tiny box. In the classical world, the electron would happily rattle around, bouncing off the walls. If you cool the electron, it will move slower and slower. Eventually, you can cool the electron to absolute zero and it would sit at rest, not moving. But Heisenberg's uncertainty principle means that in quantum mechanics, this is strictly forbidden. As we know where the electron is, confined within the walls of the box, there is a fuzzy limit to what we can know of its speed. No matter what we do, quantum physics prevents us from cooling an electron down to absolute zero. Try as we might, there will always be some residual jiggling. On top of this, like position and velocity, energy and time are not precise things in quantum physics. And like position and velocity, how well you can determine one is related to how you determine the other. The energy of things can fluctuate over time, with small quantities appearing and disappearing on tiny timescales and very briefly breaking the law of conservation of energy. This means that even empty space jiggles, a residual energy in the vacuum that is always there. Known as the quantum vacuum, this fills the entire universe as virtual particles flicker in and out of existence. And so, in the quantum world, empty space is not really empty. Nothing, it turns out, is something. Heisenberg's uncertainty principle is a fundamental law of the universe, and yet it seems disconnected from our large-scale reality. But as we will see on the next stage of our journey, the physics of the very tiny does have big implications for the cosmos. From our very existence to the birth of the universe itself. To understand quantum mechanics' role in the universe, we are going to have to think about our sun. For many years of human history, the sun was a god. To the ancient Egyptians, the sun was Ra, king of all gods and father of creation. To the Greeks, he was Helios, who rode his chariot daily across the sky. But what powered the sun? Was it just a flaming ball like the fires on Earth? It wasn't until the mid-1800s that science started to provide answers. And it started with Lord Kelvin, determiner of absolute zero, and after whom the units of temperature are named. He was considering just how old the sun was. With the physics of the day, Kelvin deduced that our star was an immense ball of hot gas, squeezed to high temperatures by its own gravity, and there was only so much mass in the sun to maintain it. It seems on the whole most probable that the sun has not illuminated the Earth for 100 million years, and almost certain that he has not done so for 500 million years. As for the future, we may say with equal certainty that inhabitants of the Earth cannot continue to enjoy the light and heat essential to their life for many millions of years longer, unless sources now unknown to us are prepared in the great storehouse of creation. This estimate dismayed geologists and biologists. It simply left too little time for the weathering of continents or evolution of animals. But Lord Kelvin did not know about the physics of the nucleus. By the 20th century, physicists had realized that atoms had a definite structure. The negatively charged electrons orbit a nucleus composed of positive protons and neutral neutrons. But the atomic nucleus is tiny, thousands of times smaller than the atom itself. So, an immense force must be present to counter the mutual repulsion of protons crammed into the tiny nuclear volume. Unimaginatively, physicists call this the strong force. And if this force could be tapped in nuclear reactions, energy would be unleashed. Soon experimenters were crashing atoms together and outpoured copious energy. Eventually, in 1920, Cambridge astronomer Arthur Eddington put 2 and 2 together. He decided the power of stars lay within the nuclei of atoms. Stars, including our Sun, are mainly hydrogen, the simplest element in the cosmos. Throughout the 1930s, physicists realized that starlight must be generated by nuclear fusion. This is when lighter elements, like hydrogen, are bound together by the strong force into heavier elements. But just how did this work? There were clearly 2 forces to worry about. Firstly, the strong force responsible for binding the nuclei together. But the strong force only acts over very short distances. 2 nuclei must essentially touch for the strong force to latch them together. As the nuclei are composed of positively charged protons, they repel through electromagnetism. For fusion to work in the Sun, nuclei must be thrown together hard enough to overcome the electromagnetic repulsion and for the strong force to grab on. But there is a problem. The core of a star is crushed to incredibly high temperatures by the weight of the star pressing down. Astronomers have calculated a newborn sun would have a central temperature approaching 15 million kelvins. But at this temperature, the collisions between protons, the nuclei of hydrogen, is just too gentle. The electromagnetic repulsion keeps the protons too far apart for fusion. So, how could the Sun possibly shine? And this is where the tiny quantum world comes in. The answer was given by an enigmatic scientist, George Gamow. Born in Odessa when it was part of the Russian Empire, Gamow was a true polymath. His mind roamed from the birth of the universe through radioactivity and into how DNA stored information. But for our story, it is Gamow's insight into quantum mechanics that matters. He realized that we cannot treat colliding nuclei like solid balls of matter. Due to Heisenberg's uncertainty principle, at the quantum level, everything is fuzzy. When 2 nuclei collide, they are not simply a certain distance apart. They are many distances apart, instantaneously. And somewhere in this fuzzy mix, they might be close enough for the strong force to do its work. Through quantum uncertainty, the 2 nuclei overcome the barrier of electromagnetic repulsion, allowing them to fuse and release their nuclear energy. This tunneling through such seemingly impenetrable barriers is a feature of the quantum world. And it is this that allows the Sun to shine. Following these revelations, throughout the 40s and 50s, astronomers steadily uncovered the secret lives of stars, spurred on by the surge in nuclear research throughout the Second World War. They pieced together the complex web of nuclear burning, firstly from simple hydrogen into helium, then helium into beryllium and carbon, and then onto heavier elements. But even with the help of quantum physics, nuclear reactions are fickle. Very massive stars are needed to create heavier elements, from carbon and oxygen and up to iron. It is only in their cores, crushed to immense temperatures and density by their weight, can the extreme conditions needed for this nuclear burning occur. These elements are essential for our existence in the universe, but of course they are useless, locked away, buried deep within stars. It is only at the end of a star's life that elements can be released. And just as the seemingly tiny, macroscopically irrelevant world of quantum mechanics gives them light, it can propel these elements into the cosmos in spectacular fashion. The neutrino is a curious particle. with virtually no mass and no charge, and so is invisible to all electric and magnetic fields. It is also blind to the strong force that binds the nuclei of atoms together. In fact, neutrinos only feel the weak force, the strangest of all the fundamental quantum forces. Posited by Wolfgang Pauli in the 1930s, due to their incredible elusiveness, it wouldn't be another 25 years until neutrinos were finally captured in an experiment. This is because, with only quantum weak force interactions, the neutrino simply ignores most matter. It will happily travel through a light year of lead before there is a chance of it interacting with a single atom. And yet, they play a crucial role in supernovae, the death of massive stars. In the immense crush of a collapsing giant star, electrons are forced into protons, and this radioactive decay spits out neutrinos. Huge numbers of neutrinos try to escape the star, but finding themselves in a superdense environment, they slam into the infalling layers, and by sheer numbers, they reverse the collapse and rip the star apart, spewing the diverse elements back into the cosmos. Clearly, quantum physics is written into the operation of the universe. Through its role in generating solar heat or recycling elements across the cosmos, it is essential for our every existence. But it doesn't stop there. Could quantum physics play an even larger role? Do we only need to think about the quantum nature of the extremely tiny? Or is there a bigger question we should be asking? Is the entire universe a quantum object? In quantum physics, the wave function encapsulates all the information in an object. But two individual objects are not described by two individual wave functions. Instead, we use a single wave function to encompass both. In fact, in quantum theory, we can use a single wave function to describe any number of particles. This raises a huge question, one of the biggest possible. Could we write down a single wave function to account for the quantum state of the entire universe? A wave function to account for every particle of matter and photon of light? It would be truly immense, but at the very least, theoretically possible. Consider the world of classical physics. Imagine you could know the precise location and speed of every atom and photon at a particular instant. Impractical, but possible in theory. With this information, you could use the laws of physics to calculate where every particle will be in the future. This is because classical physics is deterministic, and with it, the universe ticks like clockwork. The future is completely written into the fabric of today. Quantum physics, on the other hand, is built on probabilities. Knowing the wave function today will tell me the wave function tomorrow, but not a single definite tomorrow, a whole host of possible tomorrows. Which of these follows the true future path of the universe? Physicists are unsure. And in the 1950s, Hugh Everett III proposed a radical solution. In his many worlds viewpoint, he decided that there was no single future for the universe. Out there in this multiverse of universes, there are other versions of you. In some universes, you may have won the lottery. In others, you may be a rock star or a famous actor. And of course, in some, you are absolutely identical. Everett's ideas were too radical for the time, and, unappreciated, he eventually left science. But the notion of a wave function for the entire universe did not leave with him. Even Stephen Hawking pondered whether a quantum universe could solve one of the great mysteries, namely whether the universe had a beginning. Working with Jim Hartle, he deduced that in the early universe the quantum nature of time was indistinct. With this, time only really came into existence when the universe became more distinct. The singularity that dogged classical cosmology, written in relativity, just didn't occur, because there was no real time when it could have. As you can imagine, not everyone is happy with this picture, and debate continues to rage. And indeed, that is far from the only way quantum physics has been implicated in the beginning of our universe. To find out more, we must travel back in time. Back to the first trillionth of a second of existence. In the 1970s, physicist Alan Guth had a problem. He had something he needed to hide. Magnetic monopoles. They are the magnetic equivalent of electric charges. And, like electric charges, which can be positive or negative, these monopoles would be purely north or south. But this should strike you as strange. Every magnet you played with at school always had both a north and a south. You never get just a north or just a south. So why was Guth thinking about them? And why did he need to hide them? Guth was and is a cosmologist and was thinking about the very early universe. In its super-hot, super-dense state, many physicists thought that the laws of physics should be simpler. Instead of there being four distinct fundamental forces, theories suggested that there was one superforce. As the universe cooled and expanded, the superforce fractured into the current forces. Within this superforce, there should be no distinction between electricity and magnetism. With electric charges, there should also be magnetic monopoles. But whilst there is copious electric charge in the universe, there appeared to be no monopoles. If this superforce picture was correct, these magnetic monopoles needed to be hidden. And it was 1981 when Guth hit upon an intriguing solution. What if the universe underwent a rapid burst of expansion when it was very young? This rapid inflation of the universe would dilute the number of monopoles, and with perhaps one monopole in the entire observable universe, they would be undetectable. Looking at his equations, Guth saw that this inflation could explain some other features of the universe. Firstly, why it appears to be so smooth. When we look at the universe on large scales, millions to billions of light years, it appears to be the same everywhere. Why should this be the case? Just through random fluctuations, some regions should be more dense, others less. Guth realized that his inflation blew up a tiny chunk of space to the size of the universe around us. And as this tiny chunk was so small, it would have been quite smooth. And its smoothness gives us the smoothness of the heavens. And this, again, is where the quantum world raises its head. This initial chunk of smooth space would still have hosted a quantum vacuum. Within it, Heisenberg's uncertainty would still have brought energy and matter in and out of existence. And when the universe inflated, these minuscule fluctuations would have been frozen into space. As inflation ends, its energy is dumped back into the universe as matter and radiation, and the frozen quantum fluctuations would result in slightly more matter in one place than another. These differences were tiny, less than 1 part in a billion, but as the fires of the cosmic birth dimmed, gravity started to play its part. Tiny overdensities began to draw in matter from their surroundings, clumps of matter and gas began to pool until a few 100 million years after the Big Bang, they were dense enough to form the first stars. Quantum fluctuations frozen into the universe at inflation became the seeds of galaxies today. And we still see them in all their glory, written into the ancient light of the cosmic microwave background. In this theory, the quantum world has shaped our cosmos. But there is one step further back to go. Could we use quantum mechanics to confront the ultimate question of where our universe actually came from? The year is 1973, and young physicist Edward Tryon is watching a lecture by Dennis Sciama, considered one of the fathers of modern cosmology. There is a pause in the lecture, and suddenly, without prompt, Edward hears himself speaking. Maybe the universe is a vacuum fluctuation. There is a murmur of laughter in the room, and Sciama continues his lecture. But Tryon wasn't joking. And in December 1973, he published a paper with almost that exact title. Is the universe a vacuum fluctuation? Tryon was trying to unpack the bizarre implications of the quantum vacuum, how the energy in a vacuum can fluctuate over time, very briefly breaking the law of conservation of energy. And it was this that led him to wonder what the total energy content of the universe was. Clearly, all the mass and motion would be an immense quantity of energy, but there is also the potential in gravitational and other fields, and this potential energy is negative. So, he thought, if you sum up all the energy in the universe, perhaps they balance, and perhaps the total is zero. Staring at Heisenberg's uncertainty principle, Tryon realized a fluctuation of zero energy could last forever. Perhaps the entire universe was just a quantum fluctuation. Of course, this raises the immediate question of where did this fluctuation occur, which would just leave us back at the start. Where did the quantum fields come from? What came before them? We now know in our quantum universe it is possible to draw something from nothing. But what could happen inside a true nothing, outside of time and space, still remains a question beyond the borders of science. Despite this, though we can't speak with certainty of what happened before, it is clear that within the first tiny moments of existence, quantum mechanics inevitably played a role. But what about the very end of time? Could the distant, unimaginably vaster universe too be shaped by the quantum? When the universe was young and energetic, it made stars in abundance. Half the stars that will ever exist were created in the first few billion years. Over the last 9 billion years, almost all the remainder were created, and as the universe ages, its ability to create stars is rapidly diminishing. In the future, only the final 5% of stars will be born. But as we have seen, stars don't live forever. Massive stars live for millions of years. Stars like the Sun can last for billions. In time, only the puniest of stars, feeble red dwarfs, will exist. These tiny stars burn through their nuclear fuel extremely smoothly. They can live for tens of trillions of years. but eventually even their nuclear fires are extinguished and they die. All that will exist will be a dark husk, slowly losing its heat into the dying cosmos. Of course, the forces still operate and gravity will continue to squeeze and squeeze. And without the steady flow of nuclear energy, you might expect that gravity would crush the dead star out of existence. But something stops this seemingly inevitable collapse. And again, Heisenberg's uncertainty principle is the source. As the star cools and loses its energy, in its heart, gravity squeezes electrons and protons closer together. For any individual electron, the room in which it can jiggle about gets smaller and smaller. In terms of quantum physics, the electron is being constrained to a tiny volume. And this means our knowledge of the electron's speed becomes larger and larger. Even at a temperature of absolute zero, quantum mechanics ensures the electrons keep jiggling, meaning the electrons now have a quantum pressure, known as degeneracy pressure, that halts the gravitational collapse. And so the dead stars sit there in the darkness for eternity. But not quite. On immense timescales, the question arises about the very stability of matter. Whilst protons seem eternal, there are hints that they are not. Some scientists think that other undetected forces might exist, hidden in the universe. On timescales of 10 to the power of 36 years, their presence could become apparent. The action of these forces could cause protons to disintegrate into simpler particles. And so finally, the matter in dead stars would simply melt into darkness. Once they are gone, only black holes remain. On the face of it, being just distortions in time and space, these might seem impervious. But quantum physics ensures their time is also limited. The culprit again is Heisenberg's uncertainty principle, in particular the fluctuation of energy in apparently empty space. It was Stephen Hawking who first realized that the quantum vacuum spelt doom for black holes. The mathematics of the quantum vacuum is quite complex. It can be envisaged as fluctuations in the quantum fields of all particles and antiparticles together. One particularly strange aspect is that whilst the waves of particles are moving forwards in time, the waves of their antiparticles are moving backwards. In a random chunk of vacuum, these waves almost cancel. But near a black hole is not a random chunk of vacuum. Its presence, where you can fall in but it is impossible to escape, firmly separates the past and future. And this disrupts the state of the quantum waves in the vacuum. Some of the fluctuating fields are no longer cancelled. With this, the virtual particles become real particles, tapping into the energy of the black hole. As the particles flow away, the black hole steadily evaporates. It is here we seem to reach the end of our cosmic journey. But is there more to tell? In 1958, physics was abuzz. Rumours were swirling about a theory of everything. This theory would unite quantum physics with Einstein's gravity under a single mathematical umbrella. Physicists had known for decades that the language of curved space-time and the probabilities of quantum mechanics were simply incompatible. A theory of everything could open new doors on the universe. The proposers of this theory, Heisenberg and Pauli, were giants of quantum physics. They were now part of the old guard rather than the young men who had discovered neutrinos and created the principle of uncertainty. But maybe, just maybe, together they had seen through the mathematical fog and cracked the problem. Pauli was invited to speak on this new theory at Columbia University. A group of physicists travelled from Princeton to hear the great man explain his ideas. But as the lecture unfolded, everyone in the room realised it was a lost cause. The idea that all particles are actually different guises of a single, truly fundamental particle could not be correct. Freeman Dyson said, "It was like watching the death of a noble animal." Indeed, many great physicists have been obsessed by a theory of everything. Einstein was excited when Theodore Kaluza added electromagnetism to his general theory of relativity, but the excitement waned as it was realized that including quantum mechanics was fraught. Nevertheless, Einstein didn't give up, with multiple attempts to derive a theory of everything before his death in 1955. Of his attempts, he wrote, "Most of my intellectual offspring end up very young in the graveyard of disappointed hopes." This search continues today, and strangely it is frustrated by scientific success. Einstein's general relativity remains the most accurate description of gravity. Your GPS is testament to this. And for the other forces, the strong, weak, and electromagnetism, quantum physics is all that is required. This, too, is an amazingly successful theory. Within its modern form, known as quantum field theory, quarks are ripples in the quark field, photons are ripples in the photon field, and electrons are ripples in the electron field. The mathematics of quantum field theory accurately tells us the probabilities of how particles interact and what is precisely seen in the particles spewed from the collisions at the Large Hadron Collider. But fundamentally, the mathematics of relativity and quantum mechanics are simply incompatible. In their current form, they refuse to work together. A new theory with new mathematics is essential. Physicists have therefore found themselves in a theoretical playground without experimental clues to guide them, which has, of course, led to an explosion of ideas. Perhaps the world is ultimately made of strings, whose vibrations dictate that they are quarks or electrons. Perhaps loop quantum gravity is correct, with the universe knitting itself with threads of space and time. Perhaps we are fundamentally membranes floating in an 11-dimensional sea. Or perhaps none of these is the true path to enlightenment. Our century-old search for the theory continues, and we have no idea when it will end. But let's pretend. Let's imagine that we have our theory of everything, gravity and quantum physics written in a single language. What secrets of the universe would it reveal? The first place we will look is into black holes. With only general relativity, all the mass in a black hole is squeezed into a single point of infinite density, and infinities really have no place in physical theories. The hope is that within the theory of everything, this infinity never occurs, prevented by the action of the quantum. And there is another infinity that dogs Einstein's relativity. The infinity at the birth of the universe. At the moment of creation, the cosmic density was infinite, and it is this infinity that stops us from peering before the Big Bang. It stops us from knowing where our universe ultimately came from. It stops us from knowing what came before. Hopefully, the theory of everything will open this locked door. Perhaps it will reveal that we were born from a previous incarnation, a universe before our own. Perhaps we will find that we are lost in the multiverse, just one universe of countless others. Or perhaps we will pry open the door to find ourselves staring into an abyss, an aberration born from a random fluctuation, our existence little more than a quantum dream against a backdrop of unending nothingness.